Okay, so before talking about the amplifiers, it's actually good to have a little bit of a discussion, although brief, about biasing. The discussion is very similar to what we did with BJT transistors, meaning that, well, we know we need biasing simply because if I take a MOSFET and connect the signal source to the gate of the MOSFET, and if this signal source, let's call it Vin, if the Vin is, let's say, a small sinusoidal with an amplitude of like 1 millivolt, right? Um, if I want an amplifier out of this, well, I'm not going to get a good one at least, right? And the reason is that simply because, well, I know that for this transistor to work like an amplifier, I need to make sure that the transistor is first on, right? And I need to make sure that it is in the saturation region, right? Similar to the BJT transistors, that over there, we needed to actually make sure that the transistor is on and it is in the linear region before actually being able to amplify. Why? Because if you remember with the BJT transistors, we had this plot that we had this exponential exponential curve or exponential relationship between the VBE and the IC. And I knew that, well, the GM of my transistor, which pretty much sets the gain, is the slope of this curve, right? So knowing that, and knowing that, well, if the voltage at the base emitter or the base emitter voltage or the voltage at the base is in the order of like 0 volts or a few millivolts or even a couple of hundreds of millivolts, the slope is actually pretty small. The curve is still pretty flat, and if I want to get a good gain, I have to be somewhere around here, and we found out that somewhere around here means somewhere around like 0.7, zero point 0.8 volts, okay? So we have a very similar kind of a situation with MOSFETs. So if I want this thing to work as an amplifier for me, I need to make sure that it is on, the transistor is on, and it is in saturation, right? So if this is VGS of the MOSFET, and this is the ID, the drain current, I know that I don't have an exponential relationship, I have a quadratic relationship, but still the same definition, same story. So I care about the slope of this curve as we defined the GM last time. So I know that I have to be, if I want a good and decent amount of GM, I have to be somewhere around here, right? So that means that in addition to this signal source, I need to have some sort of a DC source on top of it, and I'm going to call that V bias, right? So I need to have something that, let's say if the threshold of this transistor is 0.5, this should be somewhere a little bit more than 0.5, right? So that the transistor is on, and then I put my signal on top of the DC voltage at the gate, and then I'm hoping that I'm going to get a good gain. How do we calculate the gain? Well, that's the topic of today's discussion. So we'll get there in a few slides. Now, the problem is that why do we need biasing? Simply because, well, I cannot have a single voltage source or a single, think about these voltage sources as a battery, right? Although we do have circuits on the chip that you can use transistors based circuits to actually generate certain DC voltages. But for now, for the simplicity and for the sake of this course, let's just assume that this is a battery, right? So if it is a battery, then you would know that I cannot have a single battery for every single transistor that I have on my chip, simply because, well, on my chip I might have millions or billions of transistors. You can imagine that for biasing them, I don't want to have like a million or billion batteries because, well, the chip is not going to be 1 millimeter squared anymore. It's just going to be like maybe 1 meter squared, right? So, or even more than that. So I have to find a way that without using a battery, without using a voltage source, somehow I have to bias this transistor, right? And we learned a few tricks or a few circuits when we were discussing BJTs, and we're going to be basically talking about similar kind of circuits or similar kind of ideas for MOSFETs. Okay, so here I'm actually showing two different biasing circuits, and I'm going to compare them in terms of like basically their simplicity and then basically their sensitivity to certain variations. So I'm going to call the circuit on the left the simple one, but the sensitive one. And the one on the right, I don't want to call it complicated because it is not complicated, but it's not simple, right? So I'm going to say that it's the, let's say, less sensitive one. and well, let's say less simple. And we're going to talk about what does that mean, right? So let's talk about the one on the left. So this circuit is very similar to the resistive divider that we had in the BJT, and it's actually much better than that. Why? Because we know that the gate of a transistor, at the gate, we have zero current. We talked about this. So I gate is always equal to zero, at least at DC, or at like basically, yeah, at DC frequencies, we don't have any current flowing through the gate, right? Simply because there's a capacitor there. Remember, when we build a transistor, we said that I have an oxide layer, which was an insulator on top of that, I put the gate, right? Unlike the drain and source, which were connected to some metallic kind of a contact, the gate was connected through this capacitor, right? It had a metallic contact on the top or poly contact on the top, but then there was this insulator here, so there's no way that we have a DC current flowing through the gate. Why is that good? Because now I can, without any approximation, I can say with confidence that the I1 and I2 are equal, right? Simply because of KCL. So all those kind of approximations that we did with the BJT, well, we don't have to do that anymore, okay? Now, because of that, I can say the Vx here is going to be just R2 over R1 plus R2 times VDD. Great. Now, since I know that the drain current of a MOSFET or drain source current of a MOSFET in saturation is half mu and Cox W over L VGS minus VTH squared. And now that I realize that VGS, or at least my VG, the gate voltage, is basically this expression, I can rewrite this current as 1 over 2 mu n Cox W over L, and then instead of VG I can write R2 over R1 plus R2 VDD minus VS, because it's VGS and this expression is just VG, so VG minus VS minus V threshold squared. Okay. Now, why did I write it in this kind of a form? Simply because I know that looking at this expression, I can see that if for any reason, let's say for temperature variations, or like for example this VDD that I have here, which is 1.8, imagine that instead of being a flat 1.8, like over time, instead of having a very constant value and basically without any kind of noise, imagine I have a little bit of a fluctuation, random fluctuation on top of this 1.8 volts, right? So it's not a perfect DC, it might actually go up and down by like 5 millivolts, right? So my VDD might change. It turns out that my threshold voltage is also a temperature dependent parameter, so that might change. Also, some of these stuff might also change during fabrication. So you design your transistor and your circuit based on the model that you have been provided by the fabrication house, but then you send the transistor and your circuit to your chip to fabrication, and it comes back and the mobility is not exactly the value that you wanted, or the W and L that you have drawn in your like physical layout kind of a drawing is like off by a few nanometers or something like that. So I might have variation here, I might have variation in VDD, and I might have variation in threshold voltage. Okay. Now, why is that important? Because, well, they're directly affecting my current, and well, there's no process to actually stop them or to control them or to basically attenuate their effect, right? So why changing current is important? Well, if I don't have a proper ID or like a constant ID, then I know that, well, if ID changes, it means that my GM is going to change. And if GM changes, well, we'll see that my gain, the voltage gain of my transistor or my amplifier is going to change, right? So this is a circuit that's pretty simple and easy to design because, well, I can set the gate voltage using a simple resistive divider, but at the same time, the problem with this circuit is that any changes in the threshold voltage or VDD or any of the device parameters or physical parameters of the device is going to be kind of like having a catastrophic kind of a consequence, right? Now, but then it is simple, not just because it's a resistive divider, It's because of the fact that I can set the gate voltage just by these two resistors. I don't have to get RD and RS involved, and this is going to be really good when we're actually designing transistors or designing amplifiers, because when you're designing a circuit, you want to make sure that, like, for example, you set this RD to set the gain. You don't want this RD to be both involved in the gain and the biasing and so many other things, right? Let's say output impedance and other things, right? Because the moment that one resistor or one parameter is actually affecting a few performance parameters, then you have to actually start thinking about trade-offs and thinking about like how big it should be or how small it should be. This RD already sets a lot of stuff. For example, it sets the gain, as we will see. It sets the limit for the current before getting saturated, because we know that the more RD I'm going to have, the more RDID I'm going to have. The voltage across it is going to be bigger. Therefore, it's going to push my VDS to be smaller. And I know that the moment VDS becomes less than the overdrive voltage, the VGS minus VTH, then, well, my transistor goes out of saturation and it's not good anymore, right? So good for amplification, I mean. So that's also important. And then on the other hand, it's also setting the output resistance. It's going to be like, what if this is my output, this is where I take V out, then you can see that, like, looking up I only see VD, looking down I see, sorry, looking up I only see RD, and looking down I see some other resistor, but this RD is going to be in parallel with that some other resistor, so it's going to be affecting my output resistance. So it is already involved in a few parameters. I don't want it to be actually involved in the biasing as well, right? Ideally, I don't want it to be, I don't want any more parameters that the RD is affecting, right? So this biasing scheme at least helps us to set the VG without involving anything else other than R1 and R2, right? And the nice thing about R1 and R2 is that, well, once we set their ratio, we're pretty much done with them. The only thing that we have to make sure that they have is, well, we need to make sure that they have actually a very large value, simply because I don't want them to affect my input impedance negatively. I'm going to talk about that when we are talking about input impedance in a few slides, okay? But the important thing about R1 and R2 is their ratio. In terms of biasing, at least, all I care about them is the ratio and making sure that they gave me the VG that I want, okay? Now, let's take a look at this other circuit, right? So for this other circuit, well, the KVL is actually written here. So it's not, as I said, it's not basically very complicated. It's less simple than the other circuit, but you can see that VDD minus RDID minus the voltage across this RG minus VGS minus RSID, because, well, the current of source and gate are the same, so I can call this one ID as well, is going to be 0, right? And that's what I wrote here. And you might wonder, well, where's the RGIG? So this should have been plus IG RG, right? If I wanted the KVL to work. But then we just mentioned that there is no IG. And we know that the current at the gate is 0, so this is 0. So basically the voltage at here and the voltage at here are equal, okay? Because there's no voltage across this resistor, simply because it doesn't have any current, okay? So as you can see, in terms of like basically writing the KVL and figuring out the relationship between VGS and ID and RD and all those kind of things are pretty simple. And then knowing that this is the current equation of the transistor in saturation, I can just basically write everything. I can plug in the value that I have for VGS into here and have everything based on ID, okay? Now, why is this good? Let's talk first about why is it good, and then we'll talk about why is it not really simple. The good thing about this is, let's say, it's about basically being insensitive or less sensitive, right? Why is it less sensitive? Let's say that for some reason, threshold voltage goes up. Let's say temperature changed and the threshold voltage changed and it goes up, right? Or, well, I can do the same practice, by the way, with VDD or other physical parameters, but let's just look at the VTH for now, right? If VTH goes up, based on the current voltage equation of a transistor in saturation, I can see that if VTH is increased, then this the expression inside the bracket decreases. This means that the ID goes down, okay? So this means that ID is reduced or decreased, right? Now, if ID is decreased, then I know that, let's call this Vx, okay? Or let's just call it X. This node at the drain of the transistor, I know that Vx is equal to VDD minus RDID. So since ID went down, Vx will go up, right? Because it's VDD minus something that is now decreased. So if Vx is actually going up, I know that Vg is equal to Vx, simply because there's no voltage across that RG. So Vg will go up. If Vg is going up, again, going back to this equation, I can see that if Vg goes up, Vgs will increase, therefore ID will increase. Okay, and that's pretty much what I wanted to do. So looking at what we did here, you can see that when the threshold voltage went up, first the ID went down, but then the consequence of ID going down was ID going up. So it's kind of like a negative feedback. So I had an initial change, which resulted in ID changing in one direction, but then because of the interesting kind of configuration of this circuit, whenever ID changes in one direction, somehow things work out for the ID to go back to the opposite direction, so and bring back the ID to the value that it had, right? And you can imagine that if this VTH was like changing VDD or changing mu n or W over whatever else, like whatever changes the ID, you can see that because when ID changes, the voltage across here is changing, therefore the gate voltage changes, and then because the moment gate voltage changes, the ID also changes again, right? And this change is going to be the opposite of the initial change, because the moment ID increases, the gate voltage decreases, therefore ID decreases. The moment ID decreases, then the gate voltage increases and brings back the ID like basically to the original value because ID now increases, okay? So this is the nice thing about this circuit, which makes it quite interesting because it's very insensitive to any kind of like basically random variations, and we like it for that. What's the problem? Well, you can see the problem is now RD is somehow related to the VG, right? I can write it down here. So VG in this circuit is equal to VDD minus RDID. So designing the circuit is kind of requires a recursive kind of a process. Let's say I started with the VG, and then I find, based on this quadratic equation, I find ID, right? And then once I have ID, I have to make sure that this ID and the RD and VDD actually works out with the VG that I chose, right? If not, either I have to change RD or I have to actually change my initial guess, and then until things converge and I find the ID and VG that I want, right? But at the end of the day, I think this analysis might have actually motivated you, or might have made it clear for you that why we're motivated to actually sometimes use this circuit for biasing. Okay. The last thing I want to tell about this circuit is that it's always in saturation. That's the other nice thing about this circuit. So with this other circuit, if I have a lot of current here, I might actually go out of saturation because it brings the drain voltage down, and it might actually, the drain source, just to remind you, the requirement for being in saturation, being in the good region of the transistor for amplification, is VDS being greater than VGS minus VTH. Okay, now VGS minus VTH is set by, well, here, and we know that it's going to be basically set independent of whatever is happening here, kind of, right? So I could have really large IDs that could take my transistor to saturation, right? However, in here, why is it saturation? Like, okay, sorry, why is it always in saturation or triode proof? Because my VD and VG are the same thing. So I can write VDS as VGS should be greater than VGS minus VTH. Okay, so for this circuit, and only for this circuit I can do that, because simply because gate and drain have the same voltage. And then this expression, or this inequality, is always valid, right? You can see that mathematically VGS is always greater than VGS minus VTH, because VTH is always a positive number, and these two are the same thing. Okay, so that's another benefit of using this. So again, sensitive and simple, less simple, needs recursive analysis, but then insensitive to any kind of variations or random variations, and also always in saturation.